you get by putting s equal 1 in this series. So if you knew the series 1 minus a half plus a third minus a fourth plus a fifth is the log of 2, which Euler knew, that would give you another computation of the residue of this at s equal 1, because you can evaluate this function to be log of 2. You know that's the derivative of this function, so that gives you the residue here. Okay, so has no pole at s equal 1, and so it somehow becomes easier to extend it to negative integers if you're studying this thing. So zeta star at 0, well, he's really going to calculate the values of zeta star, as you're going to see. And zeta star at s equals 0 looks like this. 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. And you might guess that since that alternates between 1 and 0, that the correct value of it is a half, right? And then this one is 1 minus 2 plus 3 minus 4. Anyhow, it doesn't go, it looks a little better. All right, so how does Euler calculate these values? Or how does he even define them? Because those series, as he says in the paper very clearly, look, these series are not convergent, so it's not a limit in the traditional sense of the word. So he says, look, let's start with zeta star of 0. So if instead of taking the series 1 minus 1, we thought of the series 1 minus x plus x squared minus x cubed plus x to the 4th, etc., that's a rational function. That's the power series of a rational function. It's the rational function 1 over 1 plus x. Right? And so if we're trying to evaluate this series at s equal 1, which is what zeta star of 0 is, well, we can say, well, we'll take the value of this rational function at x equal 1, right? I mean, we can't sum the series, but this function makes sense at x equal 1, right? So we'll define it to be the value of 1 over 1 plus x at x equal 1, which is a half. So that gives some justification for thinking of this series as a half, right? In other words, he takes this thing which doesn't converge. He says, well, that's the value at x equal 1 of this power series. But that power series represents a rational function which we can evaluate at x equal 1, and we take that to be the value. And if you do that, and you work out what does it give for, so we've now established that zeta star of 0, or at least we have a definition of it, is equal to 1/2. Well, what is this at s equals 0? At s equals 0, this is 1 minus 2 to the first power, right, which is minus 1. So that implies that zeta of 0 would be minus a half in Euler's world. Okay? So far, so good. Now let's do zeta star 1. Okay, so that's going to be the value at x equal 1 of the power series. And we just put an x in, right? We take it to be, 1 minus 2x plus 3x squared minus 4x cubed. Okay, plus. So far, so good? I think that's what I want.
Just for negative 1.
Pardon?
Just for negative 1.
At negative 1, thank you. At negative 1 is the value at x equals 0 of that. Okay? So, how do we get that? Well, you see, if we took this power series and differentiated it, this would be 0, this would be minus 1, this would be 2x, this would be minus 3x squared. So it's pretty close. This is equal to minus the derivative of our previous power series, which we know is represented by 1 over 1 plus x. So if we can calculate the derivative of that, that'll give us a rational function, which is this power series. And Euler does that. The derivative of minus the derivative of 1 over 1 plus x, if I did it correctly, is 1 plus x quantity squared. And so if we wanted to evaluate this at x equal 1, we'd evaluate this at x equal 1. And it has a value at x equal 1, and the value is a fourth. Right? this would be 1/4. Then we go back and we figure out, so that says that zeta star at -1 is 1/4. What do we get for zeta of -1? Because we can do that using this. Well, if we put s equal -1, this gets 1 minus 2 squared, so it's -3. So we have to divide that by -3, so we get -1/12. You get the idea? We wanted to do the next one, we would differentiate this again, right? Zeta star -2, we want 1 minus 4x plus 9x squared, minus 16x cubed, etc. Well, there's a little bit of crap involved. You have to multiply by x and blah, 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 but this also is given by successively differentiating power series. And you find that when you get to zeta, I'll let you do that, zeta star of 1 minus n has the form, the value at x equals 0, at x equal 1 of a polynomial in x divided by x plus 1 to the nth power evaluated at x equal 1, where this is a polynomial with integer coefficients. And of course, Euler took the time and worked out those polynomials carefully for the first 20 values of n. So we can conclude, if you see, evaluating a polynomial with integer coefficients gives an integer at any point. And here, we just get 2 to the n. Like here we got 1/4. So here you get 1/8 in the denominator. And consequently, he concludes, as a general result, so zeta star of 1 minus n times 2 to the n is an integer. I mean, it's better than being a rational number. He gets a bound on its denominator. The only thing in the denominator is power of 2. And then if we go over here, we see at 1 minus n, this becomes 1 minus 2 to the n. So that implies that 1 minus 2 to the n times 2 to the n times the zeta function at 1 minus n is an integer. Under this crazy definition of what the zeta function is at a negative integer. So this is really a very powerful result, because if it's justifiable, these are not just rational numbers, but this gives a very strong bound on what's in their denominator. And it's quite sharp. For example, if you take n equal 2, so you're looking at zeta minus 1, this number would be 3, this number would be 4, and it would say that if you multiply zeta minus 1 by 12, you get an integer. Oh, that's what happens. So this gives not only rationality results, but very, very strong integrality results. And the generalization of Euler's theorem, putting this 1 minus 2 to the 1 minus s is a brilliant idea, but you could have done it with anything. Namely, you could have studied could have replaced zeta of s by 1 minus p to the 1 minus s. Wouldn't have hurt, because this also has a 0 at s equal 1, and so this would have a value at s equal 1. It would value would be log p. And if we call that, maybe zeta, we'll have better notation for this later. What you can prove, when you actually have the theory set up, is that the value of this function at all negative integers is a rational number, and the only thing in its denominator are powers of p. So it only has denominator equal power of p at negative integers. And consequently, if you multiply p to the 1 minus p to the n times zeta of 1 minus n is in z 1 over p for all p. So that's a really incredible generalization of these results. So people have asked me, what will I write a paper on? What would a paper in this course be? So this would be a paper. Namely, take a paper topic. A good paper topic would be how to prove Euler's results on rationality and integrality of the zeta function at 1 minus n rigorously. Namely, you have to first extend the zeta function as a function in the complex plane, and then you have to discuss how you really calculate these values and what they turn out to be and what their denominators are and that kind of thing. And that would be a really beautiful paper, and that's all over the literature. And in fact, those Bernoulli numbers that we defined last time to estimate the calculation of zeta of 2, namely the things that came up when you tried to calculate the sum of a function defined on the integers, and we inverted the exponential series. Remember, we defined the Bernoulli numbers by this, sum of bn over n factorial to the n. So that just gives the generating function for the Bernoulli numbers, and I gave you a couple of tables of them. Let's see if I can find a table here somewhere. Here we must go here. There they are. There they are. So this series looks like 1 plus t over 2 plus t squared over 12 minus t to the 4th over 720. And you find Bernoulli numbers as b0, 1, b1 is a half, b2 is a sixth, b4 minus a 30th. Calculated. People have different conventions for Bernoulli numbers. Sometimes people put a e to the t here instead of e to the minus t, in which case there's some sign changes, but as long as you know what convention you're taking. So the beautiful formula is that zeta of 1 minus n is minus the nth Bernoulli number divided by n. So Euler noticed this in his calculate. I mean, he as I say, he did this up to about n equal 20, and actually calculated what these values were. And then he knew this from his Euler-Maclaurin expansion, and he noticed, for example, when you get to B12 and you have a 691 in the numerator and stuff in the denominator, he noticed that the zeta function at minus 11 had a 691 in the numerator. And that was like too much to ignore. That's a tracer. And so he realized he realized that this formula was probably true, although he didn't really have a proof of it. But that would be a really good paper topic, taking the zeta function, evaluating it at negative integers, proving they're rational, proving that they have this integrality property, and proving this relationship with the Bernoulli numbers. Okay? But we're going to leave it at that. Suffice it to say that since the Bernoulli numbers also turned up in the zeta function at positive even integers, let's see if I can find that formula for me. I doubt I'll be able to do that to notes, but we'll try. Must have it here somewhere. Yeah, here we go. Yeah, the formula for the values at even integers is that zeta of 2n is equal to 2 to the 2n minus 1 over 2n factorial, the absolute value of b2n times pi to the 2n. So that's a better formula than just saying it's a rational number times pi to the 2n. It tells you what the rational number is in terms of the Bernoulli numbers. And since the odd Bernoulli numbers all vanish, and I mean this series is almost the power series of an even function. The only odd Bernoulli number which is non-zero is b1, you could say that this formula also works for odd integers, except but the zeta function doesn't vanish. But this formula works for all n, namely because if it turns out that if n is an odd integer, so you're evaluating at a negative even integer, this says that it's 0, and that's true. Namely, like zeta of -2 is zeta of -4 is zeta of -6, etc. They're all equal to 0. So this formula holds in general. This formula only holds for even integers, but it was too much for Euler because he noticed that the value at zeta 2n, which had a b2n in it, was close to the value of zeta at 1 minus 2n, and that led him to guess this functional equation, which is later proved, and we're going to do it in the course by Riemann, that if you replace the zeta function by this modification of it, and called that lambda of s, so this is a function that is meromorphic and has poles at only where the gamma function has poles, and gamma of s over 2 has a pole at s equals 0, and s equal -2, and s equal -4, etc. So this function turns out to be meromorphic, and it's equal to omega of 1 minus s. And when you work all that out, that gives the relationship between zeta of 1 minus 2n and zeta of 2n. And notice that the poles here cancel the zeros of the zeta function. Zeta function is 0 at all these negative integers. So this function is non-zero with the negative integers, and it better be because it's non-zero with the positive integers. So for a while, for many, many years after Riemann proved this functional equation, people were wondering what the heck is all this gamma and pi and et cetera doing in it, and it only came about 1950 with Tate's thesis that it came to be understood that this was like an Euler factor at infinity, namely the zeta function, as Euler realized, was a product over primes, p minus s inverse. And to get a really complete zeta function, you wanted to take not just the prime valuations of the rational numbers, but also the infinite valuation, and this was somehow the factor of infinity. And to get a real functional equation, you had to use all of them. Anyhow, we'll get into that later, but suffice it to say that in Euler's paper already in 1749, he had guessed this functional equation, and he had proved it in his sense when s was an integer, and he also checked it when s was a half integer, because you can evaluate like an s equal. Okay. So that's all we're going to do, Euler. It just gives you an idea of his amazing capacity to discover interesting results. I mean, nobody in Euler's time knew that the zeta function was of any interest whatsoever. To him, it was kind of a curiosity, and he kept returning to it and proving more and more things about it. And then the great number theorists after Euler used his work a great deal. For example, Gauss, who wrote the Disquisitiones, a lot of it was him finding proofs of things Euler had either proved himself or had conjectured. Like Euler worked the last 20 years of his life trying to prove the theorem of quadratic reciprocity. He had found it, but he was unable to prove it, and that was one of the great achievements that Gauss made to start his career. And Euler had also studied the field of p elements. Euler had begun the study of what we call the finite field of p elements, and had proved, and it's an important result, that the multiplicative group of this finite field is cyclic. So this means this is the elements of which are relatively prime to p, cyclic of order p minus 1. And we give Euler's proof in our usual algebra classes. It has to do with the fact that a polynomial of degree n has at most n roots over a field. N distinct roots over a field. So Gauss and Disquisitiones introduced the groups Z mod MZ. So he introduced the notion of congruence. The first sentence of the Disquisitiones is we'll call A congruent to B mod M if M divides B minus A. So he defines congruence in the first sentence of the Disquisitiones. He shows that it's an equivalence relation, that you can multiply terms, that you can add terms, that you get a ring, and spends a great deal of time studying this ring, and in particular, Gauss studied its multiplicative group, Z mod MZ star, which consists of the classes mod M that are relatively prime to M, and determine the structure of this group. For example, if M is a prime power, and the prime is not 2, then the group is cyclic. So that's a great deal of the Disquisitiones is the structure of this group, and arithmetic over this ring. So Dirichlet was a student of Gauss. Not in the formal sense, he didn't take classes from him, but he spent his whole life trying to understand Gauss's work, and also introduced a lot of powerful topics around this group. And the next step in the theory of L functions was when Dirichlet attempted to prove that they're infinitely, for each class A which is prime to M, there are infinitely many primes P congruent to A on M. So that's this famous theorem about primes in arithmetic progressions. So Dirichlet proved this following Euler, directly following Euler. Namely, he actually proves, in fact, if you take the sum over the primes, which are congruent to A mod M, so the primes in that congruence class of 1 over P to the S, that diverges in S equal 1. That's his proof that there are infinitely many. And in fact, he proves that it's asymptotic to 1 over phi of M times the log of 1 over S minus 1 as S goes to 1. So this is the way the sum over all primes behave. And if you just take the subset of primes which are congruent to A mod M, you get 1 over phi of M, where phi of M is the order of this group, the Euler number. Okay. So there are that many classes you could take mod M, and they all give you the same sum, approximately, to asymptotic. So example, if you took M equal 4, and you took the sum over the primes congruent to 1, mod 4, 1 over P to the S, you'd get 1/2, well, it behaves like 1/2 the log of 1 over S minus 1, and the sum primes congruent to 3 mod 4, 1 over P to the S, behaves exactly the same way. That's not to say that there are exactly as many for P less than X, etc. It turns out that one always dominates the other, but asymptotically they behave as if they're equidistributed on M. That's Dirichlet's theorem. That's the main theorem. Now he discovered a whole host of other things about this. So for example, the way he did this, the way he proved this theorem, was he really studied the function that he called L chi S, which in this case was the sum, of n congruent to 1 mod 4 of 1 over n to the s minus the sum 1 over n to the s and congruent to 3 mod 4. And in general, Dirichlet introduced for each character of this group, so character, and again, this was before one had a really formal notion of group theory. So if you had a homomorphism from this group to plus or minus 1, to C star, sorry. So a homomorphism from this group to the multiplicative group of complex numbers. Then Dirichlet defined an L function analogous to Euler's, where you summed over the integers n greater than or equal to 1 that were prime to m. And instead of putting 1 over n to the s, you put chi of n over n to the s. So this is a finite group. So the values in the complex numbers, the values are roots of unity. Are roots of unity. So in particular, they have absolute value 1. And so these numerators are all of absolute value 1. So if you take the absolute value of this term, is just the absolute value of 1 over n to the s, and we saw that was the 1 over n to the real part of s. And so again, we know that this series is absolutely convergent for the real part of s greater than 1. So if you did this, you see for m equal 4, z mod 4 star is a group of order 2. So you could take the trivial character, but if you took the non-trivial character, you'd get this series, right? The things which were congruent to 1 mod 4, that's the trivial class here, the character takes the value 1. The things congruent to 3 mod 4, the character takes the value minus 1, and you get this series. That would be the Dirichlet series. Good. So to prove this theorem, he introduced these new series, which were generalizations of the zeta function that Euler had studied. And he also noted that these things had product expansions, just like the product expansion for the Riemann zeta function, or the Euler zeta function, namely in the region of convergence. This could be written as the product over the primes, which do not divide m, so that's relatively prime in that condition, of 1 minus chi of p to the minus s, inverse. And the reason is that because chi is a character, so if you write chi of p1 to the a1, pk to the ak, since it's a homomorphism, that's chi of p1 to the a1 all the way down to chi of pk to the ak. And so by expanding this out and then multiplying together, you get this in the region of convergence. So not only did it have a sum expansion just like the zeta function, but it had a product expansion. Now if you take the trivial character, take the character that takes all classes to 1, right? Then it's very close to the zeta function. You've just, instead of summing over all integers greater than 1, 1 over n to the s, or taking the product over all primes, 1 minus chi of p to the minus s, inverse, you're just summing over the integers prime to m, or you're taking the product over the p which don't divide m. So we conclude that if chi is equal to 1 is the trivial character, that this definition says that L chi of s is the zeta function times a finite product of the primes dividing m, right, of 1 minus p to the minus s. Because that would cancel out the term in the zeta function, and you just would be left at the product over the primes not dividing m, right? So it's very closely related to the Riemann zeta function, and this still has a pole at s equal 1. The residue is now changed because this is non-zero at s equal 1, and this has a pole at s equal 1. But Dirichlet is going to prove, this is the main content of his theorem on primes in arithmetic progressions, he's gonna prove that if chi is not the trivial character, then first of all, L chi S, this series, converges for the real part of S greater than 0. It doesn't converge absolutely, because if you take the absolute values, you get back to the zeta function, but it converges conditionally for a real part of S greater than 0, so it defines a holomorphic function. There, so that's a big difference between the non-trivial characters and the characters, which are trivial. And finally, he also proves, so therefore you can evaluate it at 1. And the second big thing he proves is that the value of 1 is non-zero. And in investigating the value of 1, he found the value of 1 was actually quite interesting. Just like Euler found that the values at the negative integers were quite interesting, he found a beautiful formula for the value of 1. So we're going to do that. We're going to do that. Now, I'll show you one other very cool thing he found. Namely, he found that by using these these are, by the way, sometimes called Dirichlet L series, because he invented them. And these things are frequently called Dirichlet characters in the literature. The characters of this group. We'll do a little bit about character theory in general and all that, but at least for characters of this group, complex characters, they're called Dirichlet characters, and if you take this corresponding L function, which is a very simple generalization of Euler's zeta function, you get Dirichlet L series. So he found, and I'll show you an example, which is very cool. People in Dirichlet's time were already studying the following generalization of the zeta function. The zeta function was 1 over n to the s for positive n, right? So people had studied things like this, where you summed over all a and b, which were non-zero, not both 0, 1 over a squared plus b squared to the s. That makes sense too, right? It's a positive number, raising to the s power, etc. So, okay. So this could be written as the sum over the ideals of the integers, I is equal to the IDB, 1 over the index of the ideal, let's do it that way, to the s power, right? Because the ideal, every ideal in the integers, which is non-zero ideals of the integers, the ideal is generated by an integer. It's a principal ideal, and so the index is n. Okay, now what about this? Well, this is the same thing if you sum over it. This could be written as 4 times the sum over the ideals in the Gaussian integers, which are non-zero, of 1 over the index. So in some sense, it's a counting function for ideals in the Gaussian integers. Why? Because every ideal in the Gaussian integers, as Gauss showed, was principal ideal. So it's generated by a plus bi, right? And there are 4 possible generators, generators where you change the sign of A and you change the sign of B. And the index is a squared plus b squared. Okay. And that later led, and that's jumping ahead of Dirichlet, but Dirichlet certainly knew about these kind of series. Okay. Now he proves, so let's call, if we have a quadratic field, K is, and that's the only fields that Dirichlet studied, square root of d. This would be the case d is equal to -1, where you get the Gaussian numbers, right? If you have a quadratic field, let's call the zeta function of k s. This is another generalization of the zeta function. More complicated than this because here you're just summing over positive integers. But here we're summing over ideals. Sum over ideals of the ring of integers of k of 1 over the index, which is called the norm of the ideal. Yes. So if you did the zeta function of the Gaussian numbers, you'd get something like this, etc. Okay? Now, what Dirichlet proved, and that was another one of his greatest accomplishments, is that you could reinterpret the theorem of quadratic reciprocity. Quadratic reciprocity implies that the zeta function of this field, this quadratic field, is the product of the Riemann zeta function times the L function of one of his characters, where chi is a homomorphism from z mod dz star to plus or minus 1, associated to this quadratic field k, and d is the discriminant of k. So really for the Gaussian numbers here, d is equal to 4, minus 4, for q of I. D is equal to minus 4. So that's an amazing thing which we're gonna see, that Gauss's theorem of quadratic reciprocity was exactly the same as the statement that if you took the zeta function of k defined in terms of these ideals, that broke into the product of the Riemann zeta function and the L function of chi. So, so for example, this series, if I took 1/4 of the sum over a and b of 1 over a squared plus b squared to the s, that was the product of 1 over n to the s times that the sum over n congruent to 1 mod 4, 1 over n to the s, minus the sum of n congruent to 3 mod 4, 1 over n to the s. Because this is the Riemann zeta function, and this is the Dirichlet L function for the quadratic character of z mod 4 star. So that's an amazing identity because this doesn't look at all like this. So we'll get to see how Dirichlet reinterpreted quadratic reciprocity to understand the zeta functions of quadratic fields. And then the next generation realized that the generalization of a quadratic field in this context was any field with an abelian Galois group over the rational numbers. So if you had a Galois extension of the rational numbers and the Galois group was abelian, then the zeta function of k, defined this way, the general zeta function of a number field, defined this way, could be written as a product of Dirichlet L functions. And that's the beginning of class field theory, a huge opening. And the fact that Dirichlet had all the analytic properties in hand of these L functions was enormously valuable because in the next generation, Kummer discovered a whole host of abelian extensions of the rational numbers with abelian Galois group. Namely, he showed that if you took the field generated by an nth root of unity, that was an abelian extension. And these are cyclotomic fields, and so he wanted to study the zeta functions in these cyclotomic fields, and the fact that they were products of Dirichlet L functions, which are incredibly simple series, gave a huge amount of information on cyclotomic fields. So this discussion of this discovery of Dirichlet, which initially was used to just prove this theorem on infinitely many primes in an arithmetic regression, turned out to be enormously valuable in understanding the zeta functions of number fields. And Dirichlet himself did the case of quadratic fields, this great factorization, and then Kummer and Dedekind did the case of abelian fields. So we're gonna touch on all of that. But let me just show you how cool this is. What is, remember I said this has a value at s equal 1? What is the value of that at s equal 1, right? So let's take the chi of z mod 4 star to plus or minus 1, the non-trivial character. What is L chi of 1? Well, L chi of 1 is 1 minus a third plus a fifth minus a seventh plus a ninth, right? Right? I mean, that's the series that Leibniz had found was equal to pi over 4. Now, Dirichlet and later Benedict found a formula for the residue of this function at s equal 1. Just like Euler had proved the residue of the zeta function at s equal 1 was equal to 1. They generalized that, and Dirichlet proved that the residue at s equal 1 of zeta of k of s for k, an imaginary quadratic field, I'll give you imaginary quadratic field first, was equal to 2 pi over the square root of the discriminant times the class number over the number of roots of unity. This is the order of the ideal class group, and this is the number of roots of 1, which is usually 2, but can be 4 or 6. So Dirichlet proved the formula for the residue of the zeta function, which for an imaginary quadratic field turns out to be that. Okay, now if you believe that this series, which is the zeta function of q of I, is the product of the Riemann zeta function and this Dirichlet L function, then I can calculate its residue at s equal 1 in 2 different ways. I can say, well, I'll use Dirichlet's formula. It says the residue for d is equal to 4. The residue would be 2 pi over the square root of the absolute, well, that's the absolute value, which is 2, times the class number divided by the number of roots of unity, which is 4, right? So this would be, I cancel the 2's, pi over 4 times h. Good? On the other hand, the value of the Dirichlet L function is pi over 4 by Leibniz's formula. The residue of the zeta function at s equal 1 is 1. So therefore 1 times pi over 4 has to be the residue of this function, right? So therefore h has to be 1, right? So that's an analytic proof of Gauss's result that the Gaussian integers are a principal ideal domain. I never used that they were principal ideal domain. So that's it. That gives you an idea of the sort of way these L functions interact with the arithmetic. But even if I didn't know Leibniz's formula, suppose I didn't know this, Dirichlet's class number would let me derive it and prove that the class number was 1. Why? Because the residue of this is a multiple, an integer multiple of pi over 4. But it's also 1 times the value of this. So therefore, the limit of this series has to be an integer times pi over 4, right? But the limit of this series lies between 1 and 2/3, because it's an alternating decreasing series. And the only multiple of pi over 4, which lies between 1 and 2/3, is pi over 4. So that proves not only Leibniz's formula, but it also proves, so you get an idea of how powerful these factorizations turn out to be, because then you can calculate the residue here 2 ways. The residue here times the value here, or just the residue here. Let's keep going a little bit more. Okay, so before we get into the analytic stuff of these L functions and things like that, I have to do a little bit of character theory on a general finite abelian group and Fourier duality for characters and things like that. I mean, Dirichlet knew Fourier analysis well because Fourier had just done his work on the heat equation, and Dirichlet did a lot of work on convergence of Fourier series, so that was in the back of his mind, I'm sure, when he was doing this work in number theory. So we'll abstract a little bit, and then we'll come back to these multiplicative groups. So let's just take G to be a finite abelian group. And as I say, we're going to apply it to these groups that Gauss studied. Okay. And the character of G is just a homomorphism from G to the multiplicative group of complex numbers. Character. And as I say, the values are roots of unity. If G, for example, is a cyclic group of order F, cyclic with a generator 1, so, then to give a character, chi is determined by chi of 1, the class 1, which generates this cyclic group. Once you know that, then you know chi of 2 is chi of 1 squared, right? Which is an F root of unity. And that F root of unity can be chosen arbitrarily. Any F root of unity gives me a value chi of 1, and then I get all the values of chi on G by using the fact that it's a homomorphism. So the set of all characters of G is identified with the set of F roots of unity, which is another cyclic group, but it doesn't have a canonical generator. Some people like to think it has a canonical generator. They like to think that e to the 2 pi I over f is a canonical generator, but then what is I? You know, I mean, it's silly. So, if I have a cyclic group, the set of all characters is identified with the points of this, which in fact form a group. And that's generally, this is a group under multiplication of roots of unity. And in general, the set of characters of G, all characters of G, forms another abelian group under multiplication. An abelian group under multiplication using the multiplications of C star. Namely, if I have two characters, chi 1 times chi 2, and I want to evaluate on an element G, that's by definition chi 1 of G times chi 2 of G, where this is, of course, multiplication in C star. So you can take two characters and produce a third by multiplying, and you can check that that doesn't make any difference in which order you multiply, because multiplication in the complex numbers is commutative, and you get an abelian group. And the identity element is the trivial character, chi 0, trivial character, chi 0 of G is equal to 1, all values of G. That doesn't move anything. Now, people sometimes say that the character group of G is isomorphic to G, and that's true, but it's not canonically isomorphic. Here we have G being a cyclic group, and it's true that the character group is also a cyclic group of F roots of unity, but there's no way to pick a canonical element in here, whereas in this group I had a canonical element 1. So that's in general true. It turns out that we're going to show that G hat has the same order and even structure as G, but they are not canonically isomorphic. You can't go from an element in a group to a character in general. If you can, something strange has happened. So I want to show you that the groups have the same order, at least. Okay, so for cyclic groups, that's true here. It's clear that they're not only abstractly isomorphic, but they have the same order. And to go to non-cyclic groups, I claim you have the following lemma. Suppose I have a subgroup of G, and I have a character of the subgroup. Then the claim is I can extend it, extends to a character of G. Namely, I can find a character of G which, when restricted to the subgroup H, is equal to chi. Okay, so we'll do this one step at a time. Suppose I want to get to, so if H is equal to G, I'm done. If not, you can find an element in G which is not in H, and we're going to extend to the subgroup generated by H and that element little g. And if we can extend to that, then that's all of G, we're done. If not, we can extend it to a bigger group. We keep adding one element. All right, why? How would we make that extension? Well, this element G is not in H, so let n bigger than 1 be the smallest power such that G to the n is an element now in our subgroup H. Okay? There has to be some power because we're talking about finite groups. So this element, some power of it is the identity, so that's certainly in H, and then you take the first power of it, which is in H. Well then, we want to try to define chi of G. We know what chi of G to the n is, and if it's going to be a character, that has to be chi of G to the nth power. So this is known, right, because it's in H. All right, so the only thing we can do if we want to make an extension is we take this element of the complex numbers and we have to take an nth root of it. But you can do that because the complex numbers under multiplication are n divisible. I mean, if we're on the unit circle and we have some element here, there's an nth root of it over here, right? Which is another root of unity. So we just let chi of G be some nth root of chi of G to the n, and define the extension as chi of G to the a times H, where everything in this group is a power of G times an element in H, as chi of G to the a times chi of H. And you check that that's well defined and it's a character, etc. Okay? So now notice that the extension is not unique. Because to make the extension, we have to take an nth root of this element. There's no canonical nth root. There are n different choices of an nth root, n possible choices. And so what can we say? So if you think about what we're doing here in terms of this character group, we're saying that there's a map from the character group of G to the character group of H by restriction, restricting the character to the subgroup. And this little lemma shows that that map, which is a homomorphism of groups, is surjective, right? And its kernel, what's the kernel? Well, it's all things that, all characters of G that restrict to the trivial character of H. So that would give us a character of the quotient group. And conversely, any character of the quotient group extends to a character of G trivial on H, so that's the kernel of the homomorphism. So we get an exact sequence like this. And now we prove that the character group has the same order as G and is isomorphic to G and that kind of thing by induction on the number of cyclic factors of G or something like that. I mean, it's true for cyclic groups here. And suppose G has got a cyclic quotient and a cyclic kernel. Well, this would have the same order as H. This would have the same order as G mod H. So therefore, this would have the same order as G. Okay?
You prove this just by taking the H, the group exact sequence and take comp, and then
you gotta prove that harm is subjective. I mean, you see, this is not a complete triviality that you can, the map from here to here is a subjective map. I mean, this is, harm HC star, this is harm, I mean, taking harm isn't always a subjective thing, there's cohomology. So in this case, it turns out to be subjective. But what's nice is that there's a map from G to the dual of the character group of the character group. It takes an element G, and it takes it to the following character on the character groups. It takes chi to chi of G. I mean, it's just like double duality for vector spaces. And by using this exact sequence, you can show that this is an isomorphism. So G is canonically isomorphic to its double dual, but not necessarily to its dual. Now, what we're going to do when we do Fourier analysis is we're going to study a function. We're going to take functions from G to C and convert them. We're going to define a Fourier transform, which will be a function from the dual group, the character group, to the complex numbers. That's what Fourier transform does in general for abelian groups, or more generally, not just finite abelian groups, but locally compact abelian groups. And the Fourier transform, well, we'll define it as the Fourier transform of chi is the sum over G, I'll do it this way, of chi of G, f of G, and I'll put a complex conjugate over this. So I have a function defined on the group, and I have a character. I sum over the group the values of that character times the values of the function. That's called the Fourier transform of the character. And next time we'll develop all kinds of stuff about the Fourier transform and then get back to characters of this group and Dirichlet's L functions. Okay? A very nice treatment of this, if you want all the proofs written down carefully, is in Sayre's book, Course in Arithmetic. He does a chapter on Dirichlet's theorem. I won't prove everything there, but I'll wave my hands at it. And another very, very good topic for a paper, by the way, is this formula for the residue of the zeta function. If you didn't want to be too ambitious, you could do it for imaginary quadratic fields. If you wanted to be ambitious, you could do it for an arbitrary number field where there's some more complicated terms in it. That's a beautiful exercise in what's called geometry of numbers, and that's in Samuel's book. So that's generally called Dirichlet's class number formula. We'll get there, but that would be a really good subject. Good? Okay, see you next week.
C starts invisible, so C is.
That's right, that's why it's, okay, but it's not true for Ham in general, that's all I'm saying. Into a divisible group, absolutely. And I'm just writing down a proof of it.
The fact that G is not have any consequences.
It's just that there are cases where G is canonically isomorphic. The real numbers canonically, their own. And then you can say, well, by the function of the real numbers, it's Fourier transform is also a real number.
But I'm just saying.
But in general, you have to remember that you have a function of the Fourier transform, it's on another group. And so you have to do it twice to get it back on the group. And then you have the Fourier transform. It's just a good idea to keep the two different. It might be isomorphic. Okay? You can assume, so what Kate does in his thesis is very good. We're going to use the following.
All that's for
I mean, they're not hard to prove.
all the
I mean, you want to prove
all the
the
theorems,
summation
nice.
or
which are
It's not impossible.
So he actually stays like
two or one to
You
one.
can do that.
Saying
If you want to, if you want to say,
one to be two to
look,
the
do it
n,
in
something weird like this, I just said all of
course,
them.
that's fine.
With just
Okay?
one line, in
That
one
would be a
page.
wonderful topic
Yeah.
for more advanced,
So,
where you
I was
really
like,
do
I
all
was like,
that.
is this real?
Or
I think I
would
have
talk
some
about the
convergence
Adele,
issues,
you know,
what's
say,
happening.
"Ooh,
I think
I'm
about my
not gonna do all
manipulations,
those
like
things."
somewhere
We
maybe
learn a lot
I said something